Okay, let's begin. So the subject of this week's lecture is the cosmic microwave background, or the CMB. We'll begin with some history on how the CMB was observed, and then we'll discuss two phases in the very early history of the universe. When the universe was about 380,000 years old, the sky imprinted, and that imprint we're observing today, the microwave radiation, is this background which permeates the entire universe. So we'll discuss the physics of recombination in the early universe, and then we'll discuss what temperature fluctuations in the CMB are and what they mean, and what they can teach us, and we'll finally discuss what causes these fluctuations in temperature. So this lecture is largely based on chapter 9 of Ryden's textbook. Okay, so cosmic microwave background. Or CMB is essentially as far back in time as we can directly see. So all of our observations of the universe, direct observations of the universe, are subsequent to the measurement of the CMB. Everything else we know about the universe from earlier times is inferential. There are very strong reasons, very good reasons, for believing the stuff we believe about the early universe, but we only have direct observation of the CMB and everything that after the CMB was formed. So let's, because the story is charming and instructive about the nature of science, let's discuss how the CMB was first detected. So, as history lessons do, we start at the beginning. So a long while ago, the universe began. More precisely, this happened 13.798 plus or minus 0.037 billion years ago. And the universe was dense and hot. So it's dense because the scale factor, A of t, is much smaller than it is today. And it's hot because, as we've seen, temperature is proportional to A of t inverse. So it's since expanded, meaning it's gotten a lot less dense, and because of the expansion, it's since cooled. So how hot is it today? Can we measure that? So, in other words, there's an ambient radiation that underlies the entire universe. So we inhabit a bath of radiation. How hot is it today? So gamma and alpha in 1946, and Herman in 1948 predicted the existence of this ambient radiation throughout the universe. In 1964, Novikov and Droskevich claimed that this is measurable, and Dickey, Peebles, and Wilkinson in parallel started to set out to look for it. The breakthrough came at Bell Labs. So at the time, the big telephone company in the United States, Bell, named after Alexander Graham Bell, had a research wing. And it's a research wing of the AT&T phone company. And the research wing made extraordinary breakthroughs in many areas of physics and engineering. And they had, in particular, two guys, Penzias and Wilson. And these guys were interested in horn antennae that detect radio waves that bounced off the Echo balloon satellite. So they found that their signal had some noise, and some noise was impossible to remove. So we have these horn antennae, and they found that there was this noticeable, low, steady hum in their instrument, and they were able to eliminate interference in the detector due to radar, to radio, to various other things. They cooled it with helium to 4 Kelvin. And they found that no matter what they did, this steady hum persisted, whether it's day or night, whether it's wherever the instrument's pointed, it spread out across the sky. So the question is, what caused this this hum? They found that it's evenly spread out across the sky. So they thought maybe it's their instrument that's is doing something funny. And they discovered that there were pigeons nesting in their instrument. So accompanying the pigeons, there was this white dielectric, and once they removed the bird shit, they found that the noise still continued to remain in their instrument. And they noticed the noise is outside the galaxy. They detected it at a wavelength of 7.35 centimeters, which translates to 4 gigahertz, which is the microwave. And they couldn't figure it out. So Penzias and Wilson in Bell Labs, which is in New Jersey, went down to Princeton University, and they happened to talk to Dickey and Peoples. And Dickey and Peoples informed them that this is exactly what they were looking for, this ambient radiation that in which the entire universe sits. So the result was a pair of publications, one by Penzias and Wilson, and one by Princeton group, Dickey, Peebles, Roll, and Wilkinson, on the cosmic microwave background. So many, many years later, 1978, so the papers came out in the Astrophysical Journal, and this was in the 1960s. In 1978, Penzias and Wilson got the Nobel Prize for discovery of the cosmic microwave background. So the CMB is a remnant of the Big Bang. Whence the universe began. And interestingly enough, Olbers, who in his famous paradox predicted that the night sky should be as bright as the sun, and the fact that it isn't is telling us something profound about, for example, the age of the universe. Olbers was right in a sense, in that the universe is always has this this hum in the background. It's just you can't see it in the visual. You need to go to the microwave in order to see this this background noise. So, since the discovery, the cosmic microwave background was extensively studied, and it was only with the development of satellites that we had detailed maps of this cosmic microwave background. And in fact, a lot of modern cosmology is dedicated to making sense of what these instruments measure. So at any angle, theta and phi, we have a spectrum which is an almost perfect black body. So you'll recall from statistical physics that what this means is that it radiates in a particular way. So the deviation from being a perfect black body is 10 to the minus 4, 10 to the minus 5. And the temperature of this black body is 2.72548 plus or minus 0.00057 Kelvin. So what this temperature is essentially the integral over the sky of the temperature at any particular angle. So at any azimuthal angle and any latitude, we find some temperature. We integrate this temperature over the sky, and we find the average temperature is 2.72548 plus or minus 0.0057 Kelvin. So this is slightly distorted, as distorted by things we can understand. So, fact 2 is that there's a dipole distortion. So, one half of the sky is blue shifted, meaning it's shifted to a slightly higher temperature. The other half of the sky is red shifted, so it's a slightly lower temperature. And you can ask yourselves, why is this? And if you pause to think about it for a minute, you realize that it's because of the Doppler shift. So the Doppler shift tells us that it's due to the net motion of the satellite. In fact, there are various net motions involved, that lead to different Doppler shifts. So the velocity of the satellite is about 8 kilometers per second. The velocity of the Earth is about 30 kilometers per second. The velocity of the Sun is about 220 kilometers per second. And the velocity in Milky Way is about 80 kilometers per second. And within the local group, the velocity is about 630 plus or minus 20 kilometers per second towards the Virgo cluster. So there are lots of different velocities, and these lead to various distortions in the spectrum. But we can account for these distortions and figure out the effect of these. Okay, the third thing to keep in mind is that a quantity useful to measure is delta t of theta and phi over t. So this is T of theta and phi minus the average temperature divided by T. So the if you take delta T by T squared, you take the average value of that, take the square root, this works out to 1.1 times 10 to the minus 5. So what this says is that no matter which direction you point, the fluctuation in this temperature is really tiny. And this corroborates that we have an almost perfect black body. So we'd like to understand the physics of this cosmic microwave background. So to summarize, because the universe is hot and dense, it was conjectured that there should be some remnant of this imprinted in the sky. It should be everywhere. It should look the same whichever way you point your telescope. So theorists realized this, and then experimentalists accidentally found it, and then talked to the theorists, and the field of modern cosmology is in many ways a reflection of this conversation between experimentalists and theorists. So it was noticed that this cosmic microwave background is around 3 Kelvin. It's almost perfect black body, and there are small distortions in this we can understand, and there are even smaller fluctuations after we account for those distortions. So we'd like to understand the physics of the early universe, explains where this cosmic microwave background came from, what it means when I say it's the imprint of the Big Bang, and how we can better study it, and what we can learn from studying this cosmic microwave background. Okay? So, the physics of the cosmic microwave background is described by 3 related phenomena, which we'll discuss. So, the first effect is called recombination. So in recombination, the baryonic component of the universe goes from being ionized to electrically neutral. In other words, positive charges combine with negative charges, electrons, in order to create things which are neutral. So the number density of neutral ions, of ions, charged ions, all ions are charged, becomes the number density of neutral atoms. Okay, so that's the first effect of interest. Second effect is photon decoupling. So here, the rate at which photon scatters from an electron is initially less than the Hubble parameter. So remember, the universe is hot and dense. Because the universe is hot and dense, as a photon is wandering around, it eventually encounters an electron and scatters off of it. So at decoupling, what happens is the mean free path of a photon becomes infinite. So after decoupling, the scattering effect doesn't happen because the electrons have diluted enough that this interaction is a very rare interaction. So it's at this point that the universe becomes, for the first time, transparent to radiation. So this is in fact the let there be light moment in the history of the cosmos. The third effect we want to think about is last scattering. So when did typical CMB photon last interact with an electron? So the claim is the cosmic microwave background that we see is this surface of last scattering. And whereas when the surface of last scattering was actually present, and these last scattering events happened, the universe is still very hot. And since then, the expansion has cooled it down to 3 kelvins, roughly. So the picture we can draw of the universe is the following. So this is the horizon, and we are here, and interior of the horizon is a layer which is okay. So in this region, the photons and electrons are interacting, and the mean free path of your photon was not very long. And after a while, the expansion of the universe had made things dense enough that this is the last scattering surface. And since then, photons can travel essentially infinitely, and they're coming to us from all directions. Okay? So that's the picture we have of the universe today. And the CMB then is the imprint of the sky on this last scattering surface. So it's a snapshot of the universe when it was still very young. And there's a lot of physics that's built in to the structure of this cosmic microwave background. And we'll explore some of that physics as we proceed. So we'll make some simplifying assumptions in this discussion. We'll assume, for simplicity, that during recombination, all baryons were hydrogen. Okay? And we'll define a quantity, x, as the ratio between NP, the number density of protons, and NP plus NH, the number density of hydrogen plus the number density of protons. So NP is the number density of protons, and NE be the number density of electrons. Since the universe is electrically neutral, NP equals NE. So hydrogen, in a very bad cartoon picture called the Bohr atom, looks like the following thing. We have a proton, around which we have an electron. So the proton has positive charge, the electron's got negative charge, and this is electrically neutral. So this Bohr atom picture will do for our purposes, but you should never take this seriously. It's a bad cartoon because it's wrong, and if you'd like, at some point, stop by my office, explain to you why the Bohr atom is a wrong way to think about hydrogen. Okay, so this quantity x equals the number density of protons to the number density of baryons. So the baryons here are either the bare hydrogen nucleus or the hydrogen nucleus, which is neutral because it's coupled to an electron. So because NP equals NE, this is the ratio of number density of electrons to the number density of baryons. Okay, so let's look at limits. So there are two relevant limits. One limit is x equals 0, and the limit is x equals 1. So x equals 0 means the number density of protons or equivalent number density of electrons is vanishing. So this means that we're fully neutral. X equals 1 means we're fully ionized. X equals 1, numerator equals the denominator, so NH equals 0. So you'll remember that in our cartoon picture of hydrogen, proton, electron, and if we think about some photon coming in, this photon can have enough energy to ionize the hydrogen. So we're left with then a proton, electron separately. So how much energy you need for the photon to accomplish this task? The energy, which Planck's law tells us is Planck's constant times the frequency nu, is bigger than Q. This photon will ionize the hydrogen. So the energy Q, that is the minimum energy to accomplish this ionization, is 13.6 electron volts, or equivalently 2.18 times 10 to the minus 18 joules. So this process where hydrogen plus a photon gives us proton plus an electron is called photoionization. Now the reverse process happens as well. Proton and electron can get together and form hydrogen and release some energy, and this is called radiative recombination. Okay, so let's think back to a very early time. Let's take the scale factor to be 10 to the minus 5. The universe at this point was 1/10,000th its size today. So A is 10 to the minus 5. So this tells us that Z, so 10 to the minus 5 is sufficiently big. 10 to the 5th plus 1 is roughly the same as 10 to the 5th. So Z is just the inverse of A, and that'd be 10 to the 5th. And so we can go from redshift, we can go from scale factor to redshift. And the temperature at this time is about 3 times 10 to the 5th Kelvin. And at this point in time, point in history we're looking at, the universe is about 70 years old. So, at this point, the mean energy of a photon is 2.7 Boltzmann times T, and this works out to about 60 electron volts. So this means that photons are always breaking apart hydrogen atoms whenever they happen to form. So in this epoch, X is approximately 1, because neutral hydrogen is essentially unstable due to it being hit all the time by photons. So in this epoch, X is approximately 1, which tells us NP equals NE equals N baryon, and NH is 0. So there's a process called Thomson scattering. So in Thomson scattering, we have a photon plus an electron going to a photon plus an electron. If you like, we can draw the following Feynman diagram. We've got an electron moving with momentum p, and it's got momentum p prime at the end. And in the meanwhile, it's absorbing a photon with momentum k, and emitting a photon with momentum k prime. So momentum conservation tells us that P plus K equals P prime plus K prime. So that's just momentum conservation. So I've assumed there's certain symmetries in the system, these symmetries being invariants in spatial and time translations in order to get conservation of energy and momentum. And we can ask what the cross-section is for this process. And this cross-section works out to be sigma E is 6.65 times 10 to the minus 29 meters squared. Okay? So we can compute the mean free path of a photon. So on average, how far does a photon travel before it interacts with an electron? This is given to us by the number density of the electrons and the cross-section. So if you have number density electrons as some number over a volume, and the cross-section as being an area, this is essentially the only combination of these quantities that gives you a length. So it has to be the mean free path, and this is the mean distance between scattering events. So from this mean free path, we can compute a rate at which photons scatter. So let me call this guy lambda for convenience. It's the length. So we want a rate. How do we get a rate from a length? Well, a rate is how many times is something is happening per unit time. So given we have a length here, we want something per unit time, the natural thing to do is to multiply by the speed of light. So c over lambda gives us n e sigma e times lambda. And this is, call this gamma. This is the rate at which photons scatter. Okay, so let's see if we can compute a number for this. So we know that today, number density of baryons is about 0.22 per meter cubed. So this tells us then that back then, the number of baryons, which is the number of electrons, which is the number of protons, number of densities of each, is equal to n baryon today divided by the scale factor cubed, since that's how matter dilutes with the expansion of the universe. So, plugging values in, we find that gamma is going to be 4.4 times 10 to the minus 6 inverse seconds. So a photon interacts with an electron through this Thomson scattering process about 3 times a week. Now, that's enough to keep all the hydrogen atoms that form from being unstable to this process of interaction with photons. And therefore we have complete ionization. Okay, so in order to see that this interaction is happening, this interaction is problematic for hydrogen atoms remaining intact, we need to compare this gamma to a Hubble parameter. So lambda the mean free path is shorter than c over h, the Hubble distance. So what's the Hubble distance? Well, we know that h squared over h0 squared is omega r0 over a to the fourth. This is the Friedmann equation in a radiation-dominated universe. We started off with the universe being about 70 years old. So we're certainly in the radiation-dominated phase. Crossover to matter domination is several thousands of years away. So as a result, we have h equals h0 square root omega r0 over a squared. And plugging values in, you find h, when a is 10 to the minus 5, to be 2.1 times 10 to the minus 10 inverse seconds, which is indeed much smaller than this gamma we computed. Okay. So let's make some observations. The first observation is that if hydrogen remained ionized, in matter domination, then decoupling would take place at A equals 0.023, Z equals 42, T is 120 Kelvin. So this is when decoupling happens. And at such low temperatures, the photons don't ionize the hydrogen. So the conclusion we draw from this is that decoupling is not a gradual process. Due to electron density becoming smaller with the expansion of the universe. Rather, decoupling is sudden. It's an abrupt process is caused by the number density electrons precipitously dropping during this phase that we call recombination. So let's discuss recombination then. So let's first of all be very naive So a naive guess, the temperature of recombination is Q divided by 2.7 K Boltzmann. So we just set 2.7 K Boltzmann T from the black body spectrum equal to the energy needed to ionize hydrogen. So this is equal to 13.6 electron volts divided by 2.7 times kb electron volts units, which is 8.6 times 10 to the minus 5 electron volts per Kelvin. You plug those numbers in, this works out to be about 60,000 Kelvin. And the reason why this naive guess for what the temperature is at recombination fails is because this assumes that all the CMB photons are of equal energy. That's simply not true. We know the black body distribution peaks but has a long tail. And the photons in that long tail are very energetic. There aren't very many of them compared to the number of photons with energies near the peak, but it doesn't matter. There's so many of them that these ionization events will happen anyway. So it's not sufficient to just take the mean photon energy to study the temperature at decoupling. We need to account for those very rare photons, which are still very highly energetic and still take apart the hydrogen atoms as they form. So, whereas there's an exponential fall off the Maxwell-Boltzmann distribution, there's still 2 billion photons for every baryon. So at some point, the two processes will come into equilibrium. The formation of hydrogen and the ionization of hydrogen. So we have H plus gamma in equilibrium with protons and electrons. So at equilibrium, number density of the species X is some degeneracy factor times mx over k Boltzmann T divided by 2 pi h bar squared to the 3/2. So mx is the mass of species X, kb is k Boltzmann, T is the temperature, h bar is h bar. The 3/2 is there because we're thinking about three-dimensional movement of various things. Times the exponential minus mx c squared over k Boltzmann T. So if you like, this is the Boltzmann factor associated to some mass x. So Gx equals 2 when there are 2 spin states, as is the case for protons and electrons, and similarly for other species we'll encounter. So the ratio NH over NP times NE is going to be given to us GH, GP, GE, MH over MP, ME to the 3/2 power times K Boltzmann T over 2 pi h bar squared to the minus 3/2 now, since there are 2 species in the denominator, 1 species in the numerator, times the exponential MP plus ME minus MH c squared over K Boltzmann T. Here, we're working in a non-relativistic limit, so K Boltzmann T is much, much less than mx c squared for any of the particles under consideration. Okay, so we'll also notice now that the mass of the electron is much, much smaller than the mass of either the proton or the hydrogen atom. So we'll just neglect that guy. So ME is much, much less than MP, which is pretty much the same as MH. So the difference, MP plus ME minus MH c squared, this guy is nothing but Q, the binding energy for the electron and proton. So what are these scale factors? Because the proton and electron each have two spin states, Gp equals Ge equals 2. And the hydrogen is a combination of the electron and the proton. So G hydrogen is, you have two choices here and two choices there. G hydrogen is 4. So conveniently, 4 divides 2 times 2 to give 1. And as a result, NH over NP NE expression simplifies to ME K Boltzmann T over 2 pi h bar squared to the minus 3 halves exponential Q over K Boltzmann T. So this equation is called the Saha equation. And we'll use it to study physics of recombination, and we'll also revisit it next week when we discuss Big Bang nucleosynthesis. Okay. So now, let's look at X again. Okay, remember that X was NP over NP plus NH, and this is NP over N baryon, which is Ne over N baryon. So, rearranging this, NP plus NH times X is equal to NP, which implies that NH is 1 minus X over X times NP. So, the ratio NH over NP is 1 minus X over X. And now, this is equal to NE times ME K Boltzmann T 2 pi h bar squared to the minus 3 halves exponential Q over K Boltzmann T. This uses the result we just derived, I've replaced NP with NE, which I can do because of charge neutrality. And I can then compute a quantity eta, which is n baryon to n gamma. And this guy is then NP over x times 1 over n gamma. So I just replaced n baryon with NP over x. Okay, so let's compute eta. Actually, it's not compute eta, let's compute something else. Let's remember the number density as a function of the frequency. This is the energy density as a function of the frequency divided by h nu. And we saw much earlier in the course, this was 8 pi over c cubed u squared d nu over e to the h nu over k Boltzmann t minus 1. Let's define a new variable. Little x is h nu over k Boltzmann t. And the total number density is then the integral from 0 to infinity dx x squared e to the x minus 1 times a factor, which is 8 pi over c cubed k Boltzmann t over h cubed. And if we do this integral, find this equals 2 zeta of 3 over pi squared k Boltzmann t over h bar c cubed, which is approximately 0.243 k Boltzmann t over h bar c cubed. Okay, so now we know the total number density of the photons. This tells us then that the number density of the protons is equal to m gamma times x times eta. So I'm just using this expression here. So n gamma is np times x times eta. So this equals 0.243 x eta kBT over h bar c cubed. Now, we'll manipulate this a bit further. We'll write 1 minus x over x as 0.243 x eta k Boltzmann t over h bar c cubed times constants. And these constants are ME cubed here, not there, ME K Boltzmann T over 2 pi h bar squared to the minus 3 halves exponential q over K Boltzmann T. So then we divide both sides by x. We find 1 minus x over x squared is equal to 3.84 eta K Boltzmann T ME C squared exponential Q over KBT, and we'll call this quantity S. So this 3.84 is equal to 2 zeta of 3 over pi squared 2 pi to the 3 halves, which works out to 4 root 2 zeta of 3 over root pi. Numerically, that works out 3.84. So now we have a quadratic equation for x written in terms of s. So remembering our algebra, we have x is minus 1 plus square root 1 plus 4s over 2s. Okay, so at recombination, we'll take x equal to 1/2, and eta is model dependent. We'll take eta to be 5.5 times 10 to the minus 10. And solving, plugging x equals 1/2, we find KBT recombination is 0.323 electron volts, which is Q over 42, which is an important number in the universe. And T recombination works out to 3,740 Kelvin. So now we know how to convert temperatures to redshifts and scale factors. So following that cookbook for these conversions, we're able to assign some, so T proportional to A of T inverse, which is Z. We're able to find Z recombination is roughly 1370, and T recombination is about 240,000 years. And this is model dependent. These correspond to the benchmark model. So x is equal to 1 initially, stuff is fully ionized, and then later x becomes 0. So we have some plot which looks roughly like this. So from 1200 to 1600 Z, it's 1, it's 0. We have some plot which looks like this. So initially, at larger redshifts, the universe was fully ionized, and then as we go to lower redshifts or later times, the universe became neutral hydrogen. Okay, so let's try to characterize this a bit further. So you remember that the rate at which interactions were happening was NP of Z sigma E times C, or NE of Z sigma E times C equivalently. So this guy then equals x of z times 1 plus z cubed n baryon today, sigma E times C, where I've written the scale factor in terms of the redshift in a matter-dominated universe. Well, while noting that baryons dilute like matter. So we know that omega baryon today is energy density in the baryons today compared to critical density today. This is the number density of baryons today times m hydrogen c squared, since we're assuming all the baryons are hydrogen, divided by 3c squared h0 squared over 8 pi j Newton, and this is 0.04. So plugging these guys in, we find gamma of z is 4.4 times 10 to the minus 21 inverse seconds times x of z times 1 plus z cubed. So after 47,000 years, the universe goes from radiation to matter domination. So recombination happens in 240,000 years. The universe has been matter dominated for a while. So in matter domination, we know what the behavior of the Hubble parameter is. We know that h squared over h0 squared is omega matter today over a cubed, which is omega matter today times 1 plus z cubed, and omega matter today is 0.3. So then h of z is just plugging in various values for things like h0 and omega m0. We find 1.24 times 10 to the minus 18 inverse seconds times 1 plus z to the 3 halves. So, we know as well that we want to compare the rate at which things are interacting to the Hubble parameter, and the mean free path becomes infinite when the rate is such that the interactions are happening less fast than the universe is expanding. So we set gamma equal to h of z to find 1 plus z decoupling is 43 x of z decoupling to the 2/3. And we find the z decoupling happened around 1130, which implies the t decoupling was about 3000 Kelvin, and this happened around 350,000 years ago. So a more careful calculation, in fact, gives t at decoupling is 380,000 years. Okay. So this tells us then that because decoupling describes the last time photons interact with matter, the cosmic microwave background that we see in the sky is an imprint of the universe when it was 380,000 years old. So we're seeing back in time as far as that. Before that, we noted the universe is opaque, and because the interactions, scattering interactions, we don't see any further back. Okay? So, let's consider going from t to t plus delta t. The probability of a scattering event happening, dp, is equal to gamma of t times dt. And we can integrate this quantity to find the optical depth. Tau of t is the integral from t to today, dt, call it dt tilde, gamma of t tilde, since t tilde is a dummy variable. This guy is called the optical depth at time t. And we can interrogate what this optical depth is at various times. So we can as well rewrite this as tau of a is the integral from a to a0 is 1, dA tilde over a tilde dot, gamma a tilde, which is a change of variables. But this is equal to the integral from a to 1 of dA tilde, gamma of a tilde, h of a tilde, 1 over a tilde, just trading a tilde dot for h of a tilde times a. And similarly, tau of z is the integral from 0 to z, dz tilde, gamma z tilde, h of z tilde, 1 over 1 plus z tilde. Just making a change of variables. And this expression works out to be 0.0035 integral from redshift 0 to redshift z, dz tilde, x of z tilde, 1 plus z tilde to the 3 half power. Okay? The redshift last scattering, on average, is the redshift at decoupling. This is a statement on average because each individual photon may have last interacted with an electron at a slightly different time. So rather than the last scattering surface, we should think about a last scattering layer. And instead of Z decoupling being 1130, for a particular photon, it could very easily be 1100 or 1170 or whatever. Okay. So Z last scattering is in fact in some interval between, say, 1000 and 1200. All right, we've discussed right now a bunch of different phenomena. We discussed the phenomena of recombination, we discussed the phenomenon of decoupling, and we discussed the phenomenon of last scattering. So it's useful to put these things in context. So we start off a long time ago with the universe beginning, and then the universe inflates. We'll discuss inflation in a few weeks. And then after inflation, the universe is radiation dominated. And then radiation domination comes to an end, the universe is matter dominated, and various things happen. So we have a table, redshift Z, temperature T, time T. So we have radiation, matter, quality. So the crossover from radiation domination to matter domination. This happens at redshift roughly 3,570, at temperature 9,730 Kelvin, and a time 0.047 megayears. Then we have recombination, which we said was a time in which the parameter x equals 1/2. This happens at redshift 1370, temperature about 3,740 Kelvin, or 0.24 megayears. And then we have two phenomena that happen roughly at the same time: photon decoupling and last scattering. And these happen around 1100 redshift, or 3000 Kelvin, or 0.35 megayears. These numbers are somewhat model dependent, but they're roughly, any reasonable model will give you numbers in that ballpark. Okay? So that's a brief history of the first 380,000 years in the history of the universe. Let's think a little more about the physics of what's happening. So, structurally, we describe certain equations for certain phenomena. I haven't gone through all the details explicitly, but you can compute many of these details, and you get the numbers and the formula that I've quoted. So now I want to think about the physics of these phenomena a little more carefully. big ones. Okay, so we're thinking about photon decoupling as, it's useful to think about photon decoupling as the interaction of a bunch of fluids. What do I mean by that statement? What I mean is the following. So before photon decoupling, we had a photon baryon fluid. Because the photons are talking electrons and they're knocking electrons off hydrogen atoms and providing energy to put, to break apart hydrogen to protons and electrons, and conversely the protons and electrons combine and release photons. These are all interacting. So I'm thinking about this as one fluid rather than two different things. So the photons, they're photons, they travel at the speed of light, and because they're traveling so quickly through this fluid, what they do is they smooth out any density fluctuations. So they homogenize density fluctuations that are smaller than the horizon. Okay, so that's what happens before decoupling. Let's compare this to what happens after photon decoupling. After photon decoupling, the photons barely interact at all with any other stuff. They just travel with mean free path. It's effectively infinite. So the universe has become transparent, and the photons are no longer interacting with baryons. So after photon decoupling, we have two different fluids. We have photons and baryons are separate fluids. Photons don't interact, so because photons don't interact, the density fluctuations persist. So, because some regions become very dense, what happens is the hydrogen starts to collapse under its own gravity. And then subsequent to that, stars and galaxies start to form. Okay, so it's really crucial that photon decoupling had to happen in order for any structures in the universe to begin to develop. Okay, so far we've described cosmic microwave background as something observational. We've noticed certain features regarding the cosmic microwave background, that it's isotropic, essentially, And whatever temperature fluctuations there are in this cosmic microwave background is very tiny. We describe the cosmic microwave background as the surface of last gathering, the imprint of the last interaction a photon in the CMB had with an electron. And we've seen that physics describes these interactions are given to us by understanding recombination and photon decoupling. And we've seen this photon decoupling is crucial for the formation of stuff in the universe subsequent to this decoupling. Okay, so the next thing I want to do is I want to return to the CMB, cosmic microwave background itself, and examine the temperature fluctuations. In the CMB. And discuss what these things mean. Okay, so at the surface of last gathering, so the universe at this time is not perfectly homogeneous. Okay, so we can examine sizes of things by looking at the angular diameter distance. This is L over delta theta. L is the physical size of an object on the surface of last gathering. And del theta is the angular size of the object in the sky. And dA is the angular diameter distance. Okay, so we've seen how to convert this to other distance parameters. We know that at the last gathering surface, Z was about 1100. So Z at last gathering is 1100, which for our purpose is much, much bigger than 1. As a result, I'm not going to worry about these +1 factors that are floating around. So dA is d horizon today over Z last scattering, which is approximately 14,000 megaparsecs in the benchmark model, divided by 1100, which is about 13 megaparsecs. Okay, so let's use this dA, and notice that L is dA times delta theta. So this is 1300 megaparsecs times del theta for 1 radian, or 0.22 megaparsecs times del theta over 1 degree. So the instrument COBE, Cosmic Background Explorer, which first explored our cosmic background with a satellite experiment, COBE found that the largest fluctuations were about 7 degrees in the sky. This corresponds to L of about 1.6 megaparsecs. So objects of that size on the surface of glass scattering, it turns out, were not gravitationally bound. Objects of this size were not gravitationally bound. And because they weren't gravitationally bound, they were expanding with the expansion of the universe. They were moving apart with the expansion of the universe. So, let's translate this to a size. So L times 1 plus z is about 1700 megaparsecs. And this size today is larger than the biggest known superclusters. So the features in the sky on the surface of glass scattering have since expanded to enormous size today. So since the initial observations by Covey, there have been 2 further experiments that have produced a lot of CMB maps of consequence. These are the Wilkinson Microwave Anisotropy Probe, or WMAP, and the Planck experiment. In the lecture notes on the course website, you can see how the imaging of the sky in these various experiments has improved tremendously over the past few decades. We're of course waiting for the next round of satellite experiments to get an even cleaner map of the cosmic microwave background at greater resolution, and we'll discover what that teaches us. So we have a sky which is got small fluctuations in temperature. We've noticed the temperature fluctuations are 1 part in 10 to the minus 4, 10 to the minus 5. So there are very tiny fluctuations. These fluctuations are in fact there, and structures involving these fluctuations in the intervening years have grown to become enormously large. Okay? So let's try to characterize these temperature fluctuations in the cosmic microwave background. Okay, so we have delta t over t as a function of theta and phi, angle in the sky. Because these are angular functions, the natural thing to do is to expand these in terms of spherical harmonics. So L goes from 0 to infinity, and m goes from minus L to L. We have some coefficient ALM times a bunch of known functions YLM, theta, and phi. So if you expanded things like the hydrogen atom in quantum mechanics, you may have used spherical harmonics in that context. So what are these spherical harmonics? Well, let's review some mathematics. Laplace's equation tells us that del squared f equals 0. So del squared is d squared by dx squared plus d squared by dy squared plus d squared by dz squared. But since we're working in spherical polar coordinates, it's useful to write this in the form 1 over r squared d by dr r squared df dr plus 1 over r squared sine theta, d by d theta, sine theta, df, d theta, plus 1 over r squared sine squared theta, d squared f, d phi squared equals 0. And the ansatz we make for solving this equation is that f of r, theta, and phi is some function r of r times y, lm, theta, and phi. So we use some separability ansatz that we plug into this equation. And plugging in f into the equation, we find the following. We find that 1 over r d by dr, r squared dr equals some constant lambda, and 1 over y, 1 over sine theta, d by d theta, sine theta, dy d theta, plus 1 over y, 1 over sine squared theta, d squared y, d phi squared equals minus lambda. Okay? So, because, great. So, then, we can make a further ansatz. We make a further ansatz that ylm of theta and phi is equal to capital theta of theta, capital phi of phi. And this tells us that 1 over phi d squared phi d phi squared is minus m squared, and lambda sine squared theta plus sine theta over capital theta d by d theta sine theta d capital theta d theta equals m squared. So, because these are spherical functions, you want regularity on the sphere, and as a result, this m has to be an integer, and moreover, lambda equals L times L plus 1, where L is an integer, and L is greater than or equal to the absolute value of n. Okay? So now, we can write down a solution to the Laplace equation. In terms of these spherical harmonics. So, we find that r of r is equal to some constant a times r to the L plus b times r to the minus L minus 1, and ylm of theta and phi is some n e the im phi p lm of cosine theta, and the n in front is fixed by normalization, 1 over 4 pi integral over d omega on the sphere, y ln absolute value squared equals 1, and 1 over 4 pi integral, so d omega 2 is 0 to 2 pi d phi, integral 0 to pi d theta, sine theta, y lm, y star, l prime m prime is delta l l prime, delta m m prime. But it's a quantum for deltas. So this vanishes unless l equals l prime and m equals m prime. Okay. So these PLNs, these guys are called associated Legendre polynomials. And they're associated to the Legendre polynomials. So we have PLM of x is minus 1 to the m, 1 minus x to the m over 2, dm dxm, PL of x, where m is positive. And we can extend this from minus L less than equal to M less than equal to L by taking PLM of x as minus 1 to the M, 2 to the L over L factorial, 1 minus x to the M over 2, d L plus M dx L plus m, x squared minus 1 to the L with P L minus m of x equal to minus 1 to the m L minus m factorial over L plus m factorial P Lm of x. Okay, so this is some mathematics that you'll encounter in the future. I'm just telling you this for completeness. It's never going to be on an exam or anything. If you want to look at this up, if you want to use this stuff, you look it up because no one remembers this. Because I don't remember this. These Legendre polynomials themselves, okay, so the associated Legendre polynomials use PLMs. They're constructed from these PLs, which are the Legendre polynomials, and these Legendre polynomials satisfy the differential equation called Legendre's equation. Legendre's equation is d by dx, 1 minus x squared, d by dx, PL of x, plus L times L plus 1, PL of x equals 0. So PL of x, it turns out, is 1 over 2 to the L, L factorial times the L's derivative of x squared minus 1 to the L. So P0 of x is 1, P1 of x is x, P2 of x is 1/2 3x squared minus 1, etc. And these polynomials have the property that the integral from -1 to 1 dx p L of x p m of x is 2 over 2m plus 1 delta Lm. Okay? So all I've done for you is recapitulate what's in a bunch of mathematics differential equation textbooks, but it's useful to see these polynomials once if you haven't encountered them before, because they pop up all over the place. Okay, so why did we go through this rather extensive digression? Well, we want to express the temperature fluctuations in terms of some standard polynomials. So back to physics. We can take C of theta as the average del T over T along some direction m times del T over T along some direction m. Now n and m are unit normal vectors, so n dot with m is equal to cosine theta. So these are two vectors with some angle between them, and n dot m is cosine theta. So we can write this as 1 over 4 pi sum L equals 0 to infinity 2L plus 1 CL PL of cosine theta, where PL are these Legendre polynomials. These CLs appearing here, these are called multipole moments. And this is what you actually measure. So you measure temperature on an angular scale, and we take theta to be about pi over L. And we'll see that L equals 0 is a monopole. It vanishes. The monopole corresponds to the average temperature. Okay, so L equals 0. That guy's the monopole. It vanishes. It corresponds basically to the average temperature T. L equals 1. That's a dipole. So the dipole is mostly from one motion through space. We saw that one part of the sky was blue shifted, the other part of the sky was red shifted, and that's due to this dipole fluctuation. L greater or equal to 2. This tells us about density fluctuations. At the surface of glass gathering. So del T is L times L plus 1 over 2 pi times CL times the average temperature. And it's conventional to plot this delta of T versus L. So this is in the notes. When we plot this, we see this curve has a characteristic shape. So I'm plotting the angular scale, or the multipole moment. L goes from roughly 2 to 2500. And this corresponds to an angular scale roughly from 90 degrees to about 0.07 degrees. And initially there's some noise here in the signal. We find the curve goes like this, sharply up. There's a bump, and then there are other bumps, and there are little wiggles. Maybe I should draw this better. There is big bump, and then it doesn't dip quite that far down. It goes like this, and down. Okay? So the position of the first peak tells us, this guy here, tells us the spatial curvature of the universe. Whether it's positively curved, whether it's negatively curved, or whether it's flat. The second peak, it turns out, tells us about the ratio of the baryon density to the critical density. Third peak will tell us about dark matter. So analyzing the spectrum, the cosmic microwave background, teaches us something about what the universe looks like on global scales, and also what it looked like at early times. So let's say a few words about that, and then conclude. Okay, so we've noticed that there are fluctuations in the cosmic microwave background. These fluctuations should be there. These fluctuations follow certain characteristic behavior. This characteristic behavior lets us deduce certain facts about the early universe. So a natural question to ask is, what causes these fluctuations? Why are they there? So let's explore why they're there. Okay, where are we? Okay, so C over H at the surface of glass scattering is about 0.2 megaparsecs. Okay, so this gives us some Hubble length scale at the surface of glass scattering. So theta H is this length scale divided by the angular diameter distance. So this is 0.2 megaparsecs divided by 13 megaparsecs, which is 0.015 radian, or about 1 degree. Okay, so this corresponds to the peak of the delta T versus L curve. Okay? there are two kinds of temperature fluctuations to worry about. First are theta bigger than theta h. The second are theta less than theta h. So this corresponds to L smaller than 180 or L bigger than 180. Okay? So these guys are large scale fluctuations and these guys are small scale fluctuations. And these two kinds of fluctuations have different different physics at their origin. Okay, so we'll look at each of these in turn. Okay, so first large-scale fluctuations. Corresponding to theta bigger than theta h. So let's compare various energy densities. The energy density in dark matter at the surface of last scattering is omega dark matter today times the critical energy density today times 1 plus z last scattering cubed, and this is about 1.8 times 10 to the 12 MeV per meter cubed. Energy density of the baryons, the surface of last scattering, similarly works out to 2.8 times 10 to the 11 MeV per meter cubed. And epsilon gamma at the surface of last scattering, well, that's omega radiation today, epsilon critical today, 1 plus z last scattering to the fourth now, so this is radiation, and this is about 3.8 times 10 to the 11 MeV per meter cubed. So we see that the energy density of the dark matter is bigger energy density of the photons, which is bigger energy density of the matter, and the ratio is about 6.4 to 1.4 to 1. Okay? So this tells us that large scales, dark matter is a dominant contribution. Okay? Okay, so suppose the energy density in the dark matter is not perfectly homogeneous. Okay? This means that we can write the energy density at some position r as the average energy density plus some fluctuation at r. Okay, so that's the mean, and that's the fluctuation. So, if you look at the Newtonian approximation, we have some Newtonian potential del phi. This is equal to 4 pi g Newton over c squared times this fluctuation. Okay? So the CMB photon, so there's some areas that are slightly overdense and some areas that are slightly underdense. In an overdense area, we have some local minimum of the potential. And in climbing out of the potential well, so we have some minimum of the potential. In climbing out of the potential well, the photon loses energy. and consequently, it's redshaped. Similarly, if you have a photon near the maximum potential well, a photon gains energy as it rolls down the hill, and it's blue shifted. Okay. So, a careful treatment of this in general relativity is called the Sachs-Wolf effect. And del T over T at large angular scales turns out to be 1/3 del phi over c squared. So temperature fluctuations on large angular scales give us a map of the potential fluctuations delta phi at the surface of the last photon scattering. And these fluctuations in the potential are capturing the distribution of dark matter, since that's a dominant contribution to the energy density on these scales. Okay, so that's the physics of fluctuations at large scales. Now, let's look at the fluctuations at small scales. For small scale fluctuations, we need to worry about the photons and the baryons. In fact, we've got photon baryon fluid. So because we've got a photon baryon fluid, W, the equation of state parameter, is between 0 for matter and 1/3 for radiation. Okay, so suppose the fluid is in a potential well. Due, for example, in dark matter. So the fluid then falls towards the center of the well, and as it falls towards the center of the well, as it falls down to the center of the well, it's compressed by gravity. So as it's being compressed by gravity, the pressure rises. Because the pressure increases, this makes the fluid expand. Okay? So now the fluid is expanding, and the pressure is decreasing. So then, because the pressure is decreasing in expansion, gravity takes over again and compresses the fluid. So you have these so-called periods of expansion and compression, which are called acoustic oscillations. The maximum compression happens when the density is slightly higher than average. So the temperature is proportional to the energy density of the quarter and slightly higher temperature. So during expansion and compression, the Doppler effect is in play. And this changes the temperature. Okay? All right, so let's go back to the curve, which describes the multipole moments. Okay? So figuring out delta t versus L, E is model dependent. But the peaks tell us things. So the highest peak which is around 1 degree, it tells us about the potential well at maximum compression at the surface of the last gathering. So the position and the amplitude of this highest peak is extremely relevant. So in a negatively curved universe, a universe in which kappa is -1, the angular size of the object is smaller than a universe that's positively curved. Okay? So it turns out that the distinction between kappa equals -1 and kappa equals +1 is around 1 degree. Theta bigger than theta h. 1 degree. So the actual data we see is consistent with kappa equals 0, a flat universe. Okay? The first peak then is a statement about the spatial curvature of the universe. The other peaks tell us about the densities of various things. Okay? So the first peak helps us establish benchmark model. And the CMB measurements, together with the supernova measurements, suggest that omega is 1. So this is a sum of different pieces. Today we see omega matter is about 0.3, and omega cosmological constant is about 0.7. Omega radiation is negligible. So we're able to establish things about the structure of the universe today based on looking at the structure of the universe in terms of temperature fluctuations at the surface of last gathering. So the cosmic microwave background then is a window into understanding how the universe looks and behaves at various times, both early and late. Okay? So this is really all I want to say. I realize this is a rather compressed discussion, but everything is in the book, everything is in the notes, And in any case, you're going to learn most of the physics in this by working some problems. So this is basically an introduction, a summary sheet, if you like, a guide to what's important in your reading and in preparing you to actually work problems where you learn some of this stuff in greater detail. Okay, so I'll stop there. And next week, we'll pick up with a discussion of Big Bang nucleosynthesis.